Hi everyone, welcome to Modern Optimization Methods. Today we will introduce the fourth part of Chapter 9, Hypergraph Matching Problems, as well as the Quadratic Penalty Method. Now in this part, we will begin with introducing the hypergraph matching problems. Then we introduce the relaxation problem. Finally, we apply the quadratic penalty method to solve this problem. Then we conclude this part. Now let's first take a look at what is graph matching. So the idea of graph matching is that you got two images or multi-images. We try to match them together, okay? So for example, you got this point may corresponds to this point here, okay? So you try to match the corresponding points in two images together. So here, the black box here is actually the graph matching algorithm. Now, the graph matching problem has many applications in computer vision. For example, in recognition, we can apply this to face recognition, action recognition, and tracking. Also, in retrieval, we can retrieve the object or motion from a figure, okay? So this is the application of the graph matching. And if we take a detailed look at how this graph matching works, it actually contains several steps here, okay? So let me explain it one by one. So at the very beginning step, we input two images, and this is the images that we want to match. Then we use some algorithms to select the point or pixels, okay? So these points or pixels are represented points in the figure. After that, we do feature extraction. So the feature extraction basically means that we need to extract meaningful features from the pixels or points here. And we need to evaluate some initial feature evaluations in this part. Finally, with the stages before, then the fourth part is that we build optimization model to do the graph matching algorithm. Then the final output is that we put the two figures or images and we match them together, okay, by pointing some feature point to another pixel or point. So this is the main stage for the graph matching, and here the mathematical model or the optimization model part is what we are going to focus on. So we assume that the three stages before are already executed for us. Then we try to focus on the fourth step. So the aim of graph matching is that we try to match two sets of points by some mathematical model. So this is the aim of graph matching. Now let's take a look at hypergraph matching. So compared to graph matching, hypergraph matching uses more information between points. So we start with graph matching. In graph matching, we may use point-to-point matching information, meaning that we build up some correspondence between points from one group to another points in the other group. And we have some matching score called I1, I2. And if we use pair-to-pair matching, then we can include the distance matrix information, okay? So if we pick up 2 points in one set and we match this edge with the other edge in the other sets, then we can include the distance information to do the matching. And for hypergraph matching, we actually have hyper edges in each set, okay? For example, we take triple to triple matching as an example. We can pick up 3 points in one set, and this will construct a triangle, and then we match this triangle to another triangle in the other sets. Then they will get a matching score, okay? So by using the hyperedge, which contains more than 2 points, then we can include more information such as angle information as well as rotation and stretch. By using more information, we can improve the matching performance or matching result. Okay? Now, let's take a look at the mathematical formulation for hypergraph matching. So we are giving hypergraphs G1 and G2. Okay? So each G contains a set of points V1 and V2. They are sets of points representing that they collect the points in the figure actually. For example, V1 contains 4 points, and V2 contains 5 points. Alright? So we try to match the points between the two sets. Okay? And for the edges E1 and E2, they are sets of hyperedges. So what is hyperedges? As you may recall that for each edge, it actually connecting 2 points. That's called an edge. Okay, so for hyperedge, it contains more points. As I mentioned before, for 1, 2, 3, these 3 points, it contains an hyperedge. Okay? For example, 1, 2, 3 in E1 is an hyperedge. And ABC, if it contains in E2, then it is also a hyperedge. Now, the aim here is that we try to find assignment matrix X, where this X is in N1 by N2 dimensional space. Okay? So each of its elements are defined in the following. If it is 1, then it means that the L1 points is assigned to L2 points in V2. If they are not assigned, then it is 0. Okay? So in other words, in order to measure the assignment, we introduce an assignment matrix X, which is either 0 or 1, and X, the row of X, is actually the number of points in V1, and the column of X is actually the number of elements in V2. Now, let's take a look at hypergraph matching. So, matching of hyperedges, how we represent this. If 2 hyperedges, they are matched, it means the following way, that the X L1, L2, X J1, J2, and X K1, K2, the multiplication of the 3 terms is 1. In this sense, we can see that L1 is matched to L2, and K1 is matched to K2, and J1 is matched to J2. Okay, so we can find the correspondence. Otherwise, then they are not matched. Okay, so for matching score, this capital B, it is defined as the matching score between LJK1 and L2J2K2. Okay, so if assume that they have a correspondence, then they got a matching score. Okay, with 6 indices below. Okay, because for each hyperedge, you got 3 indices. So the matching score between 2 hyperedges, they got 6 indices. And we have some assumptions that for all the hyperedges in the edge set, the corresponding matching score is non-negative. And if either of the edges are not in the hyperedges, then we will set it as 0. Okay? And in our hypergraph matching optimization model, we assume that this B is available. And as we can see that this B got 6 indices, therefore it is a 6th-order tensor. Alright? Now, let's take a look at the mathematical formulation for hypergraph matching. So given the hypergraph G1 and G2, as well as the matching score B, we are trying to find the correspondence between the feature sets V1 and V2. Okay, so this is the aim of our problem. So the objective is that we try to make the sum of the matching scores achieve the maximum. Alright, so this is the objective. In other words, we can put it in terms of optimization problem. We try to maximize the sum of matching score such that this matrix X is an assignment matrix. So what is assignment matrix? It basically means that for each point in the left-hand side, it can only be assigned to one unique point in the other set. Okay, so this is assignment matrix. So if we put the assignment matrix in mathematical formulation, it basically says that for each row of this matrix S, the sum of this row must be 1. And also, X is in 0 and 1. Okay, X is either 0 or 1. We refer this to as assignment matrix or assignment constraints. So this is the mathematical formulation for the problem. As you can see that it is actually very complicated because you got so many indices in the variable, okay? And also the matching score matrix. So next, let's consider a special case that if you got the left-hand side and right-hand side the same size of feature points, then the constraints reduces to a more complicated one, that you have the column, the sum of row is 1, as well as the column of X is also 1. In other words, when you got the same size of feature points for V1 and V2, then each point on the left-hand side can only be matched to the one point in the other sets. Conversely, it is also the same. Therefore, we got 2 constraints for the special case N1 equals N2. Okay? Now, let's first try to reduce or reformulate this problem into a vector case. Okay? So recall that the variable at the moment is a matrix. So we transform this matrix X into a vector X by putting each row of X as a block in the vector X. Okay? So each row here, if we do a transformation, we put it as a one block in this X. Okay? After that, we have some calculations for the indices xj corresponding to the elements in X, big X. Okay? Similarly, we can transfer the 6th-order tensor into a 3rd-order tensor by the same calculation. Okay? Then the problem can be transferred to a more neat form, that you got a 3rd-order tensor A ljk multiplied by xl xj xk, so the sum of them. And we also transfer it into a minimization problem by adding a minus. Okay? So this is the objective function, and the constraints, now we transfer it into vector X. So the constraints is transferred to each block of X. They will have the sum to be 1, and then for each X it is either 0 or 1. So the constraint is also equivalent to the previous one. Therefore, this is the hypergraph matching problem. Alright? So if we take a look at this problem, how can we solve it to get the matching? There are some difficulties. First difficulty is that this problem is a 0-1 programming, meaning that it is an integer programming. Okay? So integer programming, in general, this is a NP-hard problem in general. So meaning that solving this problem is not that easy. So we have to be very careful to design the algorithm. There are some traditional methods to solve it, including basically 4 types. One is the power iteration algorithm. The second is the reweighted random walks method. And the third one is the successive projecting method. Okay? And the last one is the block coordinate ascent method. So the 4 methods can be summarized into 2 types. The first type is that we relax the 0-1 integer constraint into an interval or box constraint between 0 and 1. Therefore, the problem will reduces to a relaxation continuous optimization problem. And then we solve the relaxation problem. After that, we do truncation to get an optimal solution. The second way is to reduce the original problem to a series of small size of assignment problems. Okay? By doing this, they keep the 0-1 constraints. However, the size of the problem is reduced. Okay, let's make a brief summary about this part. In this part, we basically introduce the hypergraph matching problem as well as its mathematical reformulation. We also review the existing methods to solve it. In the next part, we will show how we apply the quadratic penalty method to solve this problem. Okay, we stop here and see you next time.